Okay, today we're going to cover composition of functions. So pretty much we let F be a function that assigns employees. An example, we assign a function that assigns employees to offices in a company. We let G be the function that maps each office to a telephone number for that particular office. So an employee, we'll call him, I can't pronounce him, but we'll call him Anita Bath, is assigned the office, and the function of Anita Bath is F evaluated at Anita's office. So Anita's work phone number is G. So we assign G the function to represent the phone number of Anita's Bath. The process of applying a function to the result of another function is called a composition. So definition of it, if f and g are two functions where f is mapped from x to y, and we have a g function which maps from y to z, the composition of g with f is denoted by g with a little circle in the center. That's the composition of f. Is the function g composed with f that maps from x to z, skipping the y, right? So such that for all x is an element of the set x, g composed with f, that's the proper notation, is also equal to g parentheses f of x. So you probably have seen that in college algebra. So we are going back to that just as a review so that way you understand how the process works. So here's a participation activity. So let's go through it. Suppose our set, we have a set x that maps from 1 to 3, y goes from A, B, C, and z has the elements 7, 10, and 12. So we set x mapping to y, we let x go to A, 1 go to A, 2 goes to A, 3 goes to B. Then we have the g function, which maps A to 10, B to 10, C to 12. And so how does it work? What is G composed with F? Well, since 1 goes to A goes to 10, therefore 1 goes to 10. And 2 goes to A, therefore A goes to 10, therefore 2 goes to 10. 3 goes to B goes to 10, therefore 3 goes to 10. So since f of 2 is equal to A and g of A is equal to 10, therefore g composed with f evaluated at 2 is equal to 10. So the mapping it out shows you this how the process works with mapping. If we were to do f evaluated at 3, 3 goes to B goes to 10, B goes to 10, yeah, 3 goes to 10. Um, f goes to f of 3 is B, and then the function g of B goes to 10. Therefore, f composed of f evaluated 3 is equal to 10. So that's just giving you the rundown on how mapping works. So you can see how that works. So generally, the order in which the functions apply are more important. So f composed g is not the same as g composed with f. So the order of how you're evaluating compositions does matter. So you have fog and Goff. They're two different operations. You do get different results most of the time when you do both of those. So just notation, f fog is f parentheses g of x. G Goff is g parentheses f of x. So they must define the two functions. Sometimes you may have 3, but for most of the time we have 2. So they have to define it, and notice how they define it. Reals are with positive reals, right? Positive reals. So make sure that you all see how it is defined before you begin to apply the composition functions. Here's an example of one with three. F composed of G composed of F. So you have three functions. So this is the proper notation of how to process it. So you always start with the outside first, and then you work your way in. Okay, so that's how the process works. So the identity function always maps a set onto itself and maps every element onto itself. So the identity function A denoted by I sub A, which maps A to A, is defined as A sub A of A equals A for all A element of the set A. So what does that mean? So when you find the inverse of a function and you you compose it with the regular function, you're supposed to get the value back. And it works the other way around. If you do F composed with F inverse, you're supposed to get an identity value back. So this is very important to check to see if one function is the inverse of the other. So to do that, you're supposed to get an identity back, X sometimes. All right, so let's take a look at our participation activity. Suppose a set X contains the elements 1, 2, 3, Y contains the elements R, S, T. So if I map 1 to S, 2 to T, 3 to R goes to 3, S goes to 1, T goes to 2. Therefore, 1 goes to 1, 2 goes to 2, and 3 gets mapped to 3, which is the identity. You get the same X values back. 2 to 2, and 3 to 3. We get our domain back, the identity function. Right, so suppose we have another example. R goes to 3, 3 goes to R, S goes to 1, 1 goes to S, T goes to 2, 2 goes to T. Again, we get the identity. Okay, so that's just a map of how the process of inverses work. You get the domain back. All right, so let's take a look at some examples of how we evaluate composition of functions. So remember, if we want to do fog evaluated at 2, we have to write the notation. It's going to equal to F composed with G evaluated at 2, right? So what do? Let's take a look. Let me write down the problem. If my F of X is 3x plus 1, my G of X is equal to x squared, H of X is equal to 2 to the X, and I'm asked to find fog evaluated at 2. All right, so let's check it out. So here are my givens. I want to do fog, so I'm going to write the expression F parentheses G evaluated at 2. Okay, so there's 2 ways you can do it. One, you can simplify the inside, work your way out. I usually do the out. So I start with my F of X, so I write 3x plus 1. I remove my X, put a blank. In the blank, I'm going to put in my G of X. In our case, it is x squared. And I'm going to evaluate at 2. So I'm going to substitute 2 in for the X. So this is 2 squared plus 1. Therefore, I get 3 times 4 plus 1. I get 12 plus 1, which is 13. Okay. Or you could evaluate this first. I'm going to substitute 2 in for my g of x. So that would be 2 squared. So that's equal to 4. And now I'm going to get my f of x and substitute my 4 in. So that gives me 12 plus 1. I get 13. Right, so either way, you get 13. All right, so let's take a look at it. And it is, oh, I didn't put the answer in. 13. It is correct. What about G composed with H evaluated at 3? All right, well, let's do that one. So that is G of H evaluated at 3. All right, so let me put this back up. Let's take a look at it. All right, so I'm going to go ahead and do G parentheses H of 3. I'm going to write my G of X function first. It's X squared. I'm gonna remove the X. It's supposed to be X squared. I'm gonna take out the X, and I'm gonna substitute my H. My H is 2 to the X, and I need to substitute a value of 3. So this is 2 to the third squared. So I'm gonna go ahead and compute this. That would be 8. 8 squared is 64. Whereas I can do it, or I can do G and evaluate 3 at H. So if I substitute 3 in for my X, this is going to be equal to 8. And if I substitute 8 into my G function, it would be 8 squared. And presto, I get 64. Let's take a look at it. 64. Okay. Now let's do, we get 3 of them. So they want us to evaluate F composed with G, composed with H. Evaluated at 0. All right, let's take a look at it. All right, so I know I'm going to have to rewrite this. F parentheses G parentheses H parentheses at 0. It's embedded. We got a whole bunch of embedded functions going on. So I'm going to start with my F. F is 3x plus 1. I'm going to remove my x. I'm going to substitute my g function. My g function is x squared. All right, so now in the x squared, I need to substitute my h. So that is 2 to the x. So it's 2 to the x squared plus 1. Now I got to substitute a 0 in. 0 squared plus 1. Anything to the 0 power is 1. So this would be 3 times 1 plus 1. I should get 3 plus 1, which is 4. Right? Or I can substitute 0 in for my h. So that is 2 to the first. So I'm doing F G 2 to the first is 1. Right, 2 to the first is 1. Then I evaluate G at 1. So that's 1 squared. That is 1. And now I substitute 1 into my function F. So that is 3 times 1 plus 1. 3 plus 1, you get 4. You get the same result. All right, so let's plug it in. 4. Awesome. Now they want us to find the inverse. I want to apply F. Okay, so the next one I'm going to do F composed of the F inverse evaluated at 17. All right, well, let's see. Let's take a look at it. So I gotta find my inverse first. So let's go over here and do my little thinking cloud. I gotta find the inverse of 3x plus 1. So let's find F inverse of x, right? So here's my F. How do I find my inverse? So here's, I'm gonna write my function. I'm gonna remove it. So f of x, write y, 3x plus 1. I'm gonna reorder the variables. So that becomes x equals 3y plus 1. Solve for y. I'm gonna subtract 1. Divide by 3. So x minus 1 over 3 is equal to my inverse function. All right, so I got my inverse function. Now I want to perform f composed with f inverse. So this is f inverse evaluated at 17. All right, well, let's plug in 17 into my inverse. So that would be 17 minus 1 over 3. So that would equal to 16 over 3. That doesn't seem right. 16 over 3. And I plug in 16 over 3 into my function, which is 3/16 plus 1. My 3's cancel. Now I'm left to 16 plus 1, which is 17. So I got my identity. I got my value back, which is 17. Hence, my inverse and my function kind of cancel out, and that left me with the value that I needed to evaluate it at. So it came out good. So what did the instructions say? What is f composed of f inverse of 17? That has to be 17. Awesome. All right, let's do composition of functions. Let's do that challenge activity. Let's start it off. Okay, so this one, I have the ceiling function and I have a regular function. So I'm asked to find f composed with g evaluated at 0. So I'm going to plug in 0 for x. So that would be 6. So then I would plug in 6 here. 6 over 5 is 1 point something. I need to do the ceiling. So that should be 1. Let's see. No, it's not. Huh. 6 over 5. Oh, yeah. 6 over 5 is, yeah, ceiling should be 2. You're right. It is 2. I knew that. I was just testing myself. It should be 2. All right, so let's look at this one. So I want to do f composed of g evaluated at 0. Plug in 0. That's 6. That's 4. 4 2 to the 4th power should be 16. Correct. Next one, I have a ceiling again. I want to do fog f parentheses g evaluated at 2. So I'm plugging in 2 here. That's a half. So half would be 0.5. So that should be 1. So 1 minus 6 should be -5. Oh, we have a triple. So I got to evaluate f at 2. 2 over 6 is a third. So that should be ceiling. So that should be 1. And then plug in 1 into the h. 5 times 1 is 5. Plug in 5 here. 5 plus 4 should be 9. All right, another one, given f of x is x to the third, g of x is x minus 4. Give a mathematical expression for g composed with f. Do not simplify. Okay, so f, I have to plug in the f function here. So that should be x to the third. X at 3. Yep. Cool. Next. Give a mathematical expression for f composed with h. Okay, so here's the h. I'm plugging it into the f. That should be 3 hat parentheses x plus 5. Cool. All right, the drawings below give arrow diagrams for two functions f and g. Notice it goes w to b, b goes to 4, w goes to d, d goes to 1, x goes to e goes to 4, y goes to a goes to 3, z goes to z goes to b goes to 4. What is the domain of f composed with g? Well, it starts with x, so there it is. V, W, X, Y, Z, right? Targets should be 1 through 5. Since I'm doing f composed with g, I'm going to end up here. So it is 1 through 5. And give the arrow diagram for, so they want you to write V goes to B goes to 4. So V4. W goes to D goes to 1, W1. X goes to E goes to 4. X goes to 4. Y goes to A goes to 3, Y goes to 3. Z goes to B goes to 4, so Z4. And the range goes to 1, 3, 4. Oh, sorry. 1, 3, 4. There's your range. Okay, and then the other ones are similar to the ones we did. You can work them out. Here are your solutions. A is 1, B is 121, C is 16, D is they want the mathematical expression. Remember this is ceiling, and here is E. All right. And that concludes our lesson for composition of functions.